It's great. So let's get started. So today we're starting a new section on dimensionality reduction. Today we'll be getting to probably the most important single method principal component analysis. It'll kind of be a whirlwind lecture where I'm going to review a lot of stuff I hope you've seen before, but I'm guessing not everyone has. And if you have, hopefully it's useful to get a refresher on it. But I'll cover a lot of material very quickly, so because of that, there are a few things to review. I don't want to spend too long on them because there's a lot I want to cover today. This is okay. So we so we're starting a new section on dimensionality reduction. It'll be 5 lectures, it seems. I have planned the streaming homework is due on Wednesday. Okay, so it's linked off the webpage. If you want to get to the webpage, this is the URL. You can search for my name, and then it's linked off of there because I know you can't find it off of Canvas because it's down. It is practice with the streaming algorithms. You'll be doing 2 data sets, which are long, just strings of, so I think just lowercase letters, or at least just characters, and you'll treat those as elements of a stream, either 3 million or 4 million, so still pretty small sort of data sets. And you'll be kind of just doing 3 algorithms, the sample, just estimating the frequency of items, which are the most frequent items, using sampling, Misch agrees, and the count min sketch. Each of them is pretty straightforward to implement, so I think it shouldn't be too bad. The questions for Misch agrees and count min sketch force you to kind of reckon with what do the error bounds actually mean, and so it's a little confusing to understand how to interpret what the sketch tells you from the information. And so that's what you're forced to kind of grapple with a little bit. There's a randomization in the count min sketch. I've asked the question in a way that might seem confusing, but it's so you can assume there aren't any issues with the randomness. So you assume that the sketch is accurate up to the level of accuracy that should be guaranteeable. Okay. So that, I realize I posted that without as much lead time as I usually do. So if you have trouble, if you're not going to be able to submit it on the regular time, reach out to me and I'll be flexible. Okay. Other thing coming up, the intermediate report for your projects is due a week from Wednesday. Okay. From the intermediate report, you will that'll be 1 page per student in the group. Okay, in a report, should start with the overall goal, which is your proposal, and what data set are you working with, just your data collection report. You will bring it to class on this day, and we will have peer feedback in class on that day as well. And then I will send something out soon where you will sign up to get personal group-based feedback from me during my office hours or other times during that week after this, when it's due. So I want to make sure I meet with every group and make sure you're on track. You can also come to me before, after class, and office hours anytime to get feedback, but I want to ensure I meet with every group. I find this really improves the direction and quality of the projects. Okay. Yeah. So any other questions on the midterm test? They should be available on Gradescope. Is that true? Or can you? Okay, great. So you should be able to see them on Gradescope. The median grade was somewhere in it's like in the 80s, but the average homework grade is pretty high. So average these out, and I think the grades are about where the overall distribution of final grade estimates for the class is about where I expect it to be. It did spread the students out a bit. But if there are regrade requests, you can ask those on Gradescope. Yeah. I hope they're mostly encoded in the Gradescope. If you look at the rubrics, you can usually figure it out. If you're not sure, you can let me know. If you see what the correct answer was, you should be able to tell what the right answer was. But if it's unclear, you can feel free to ask. Okay, great. Okay, as I mentioned, we are going to review a huge chunk of linear algebra for how you should view it in data science. I want to get to principal component analysis. We're going to be talking about dimensionality reduction as a whole, linear dimensionality reduction through the SVD, and hopefully we'll get to how this connects to the eigendecomposition as well. Which you'll see is all kind of the same thing, you just kind of different perspectives on it. And then you hopefully should have seen, who has not seen the SVD before in a lecture? Okay, everyone's seen it before. Okay, good. So we're going to go through it quickly and review a lot of things. And you will use these same ideas in many contexts within this section. And then we'll do some things beyond just the standard SVD-based approaches. But we'll go beyond, for instance, what is in 3190 after this lecture. All right, so the premise here is now the input to our problem. We're going to typically say as A, which will be a n by d point set. So I wrote, okay, it's the real numbers, and instead of to say some power, it's d-dimensional. I said it's n by d, and what does that mean? It means that I often think of A as a matrix for every row in AI, so I can think of A as a set of rows, AN, there are n of them, and each of them is going to be an element of RD. So this is an element of RD. There are D dimensions, and there are going to be n rows, okay? And typically draw the picture where there are more rows than there are columns, but the premise here is that the dimension of these data points, D, is too big, and I would like it to be smaller, so I would like to reduce the dimensionality here. We're going to be talking about dimensionality reduction. Okay, and in order to, it'll take me a while to state formally what the goal will be for the PCA version of this. It'll take most of the lecture. Okay, but the goal of dimensionality reduction is I'd like to reduce the dimensionality. In order to get this to work for the family of techniques we'll talk about for this lecture and maybe the next two lectures after that, is I want that each column is basically the same units and is going to be comparable. We're going to measure things such as AI, which is one of the rows, to some other point. These are both points in RD, and I'm measuring the Euclidean distance. If you remember, this is J equals 1 to D, AI J minus PJ. And because I'm summing these up, okay, because I'm applying a sum over these coordinates, the square of the difference of the coordinates, but still the coordinates, if the units are not comparable or the columns are not comparable units, this distance will not make sense at all. And this will show up in what we're trying to optimize here. So if I can't compare the units, I can't apply this whole family of techniques we'll talk about the first few lectures. We will get to, after that, how to deal with the case when I can't do this, okay, which comes up a lot. Okay, but for now, we're going to go through the basics, which are going to assume this is the case. You'll see lots of stuff online in lectures and other classes, hopefully not this university, where people apply these linear dimensionality reduction techniques on data sets where this is not true. Okay, please don't do that. Okay, good. Okay, there are these other techniques where you kind of learn a representation. Yeah, we'll get into those in some later lectures. Okay, and so kind of not full the goal, but the output of this is going to be a mapping. Okay, we'll call this pi, and I'll describe this more carefully later, which will go from RD to RK, here where K is often much less than D. So I'm going to go down to a lower dimensional space, and I'll state later what we want to optimize in the choice of this mapping. There are going to kind of be two versions of this. Okay, we're going to say pi is exactly of a data point is going to be an element. It's a little confusing. It's still going to be an element in d-dimensional space, but we'll also talk about a pi bar, which is going to be an element in k-dimensional space. These are going to do basically the same thing, and we can either represent it in the k-dimensional space or represent it in the d-dimensional space. In order to measure distance, I have to be in the same dimensional space, okay, even though it's on a lower dimensional subspace. Okay, so this is a little confusing, and I'll try and point out the difference between these two options here. But we really want this mapping to go down to a lower dimensional representation in some way. And so what that means, let's try and define that with some basic linear algebra. Okay, so first of all, we're going to be in a multi-dimensional space. And I'm going to try and draw this where you have a coordinate axis where this is the origin. The origin is the point that all the coordinates are 0, right? So if maybe this is a 3-dimensional space, and that would be 0, 0, 0, right? So 0, 0, 0, but in general, all zeros. And then we're going to have a data point, A, right? So this was in RD. Okay, and then crucially, what we're going to consider is a vector U. Okay, U will be a unit vector. So then U will be in RD. So it's a d-dimensional vector. And it's going to have the property that the norm of U is exactly 1. Okay, we're going to consider this unit vector in the space. This encodes a direction, but no length information. By specifying the length as 1, it doesn't capture any length information. And we can consider kind of the continuation of this. This defines a 1-dimensional subspace. And a really important operation is going to give us this point here. We'll call this point pi of U of the point A, okay? And how do we define that? We're going to define it in 2 steps. The first step is we're going to measure this length from the origin along here up to this point. Okay, this is going to be exactly the dot product between A and U. Remember, the dot product between A and U is equal to J equals 1 to D of AJ times UJ. So I take all the coordinates and I multiply the paired coordinates up, and I add all these terms together. This is the dot product. When U is a unit vector, it does something very special. it tells us the length along this direction here. So it's a very important property. And so now, but I want to get this point, which turns out to be A projected onto this blue line going through here, okay, on the dashed blue line going through this direction U. To get this point, I use this dot product. That tells me the length along there, but and this kind of gives me a one-dimensional coordinate, but I want to be able to get a point that lives in RD. This point is going to be the dot product AU times the vector U. So it tells me I want to be this vector, which is a d-dimensional vector. How far along that vector do I go? I go this dot product. Okay, so this, let's see, this part tells me where, and this part tells me how far, okay? And so ultimately this gives me a vector which is back in RD. Okay, so this is a projection to a one-dimensional space, but it still lives in the d-dimensional space. So now I can say measure the distance between these 2 points, or if I just put the one coordinate, just the dot product, I only get one coordinate, but I can't measure a distance to that one coordinate from the original point A. Okay, so this dot product is an incredibly important geometric operation. You should hopefully understand how this means. It's my favorite mathematical operation. I have a son named Max, and I still like dot better as an operation, but okay. Okay. So now this tells us basically, if I have one data point, I want to go down to one dimension. I have a vector U, how to project onto it. But I'm going to project down to multiple dimensions, not just one. I want to project to multiple dimensions. So I need to think a little bit kind of more complicated. So now I've got, again, my d-dimensional space. I'm just drawing 3 dimensions here. Does what live in d minus 1? U is a d-dimensional vector. So for instance, an example where d equals 3, U could be equal to, let's see, 0.6. That's the x coordinate, 0.6. The y coordinate might be 0.2. And then the z coordinate would be something like 0.5. Okay? Is this a unit vector? Probably not exactly, but if I have to square all the terms, 0.5 squared is about 1/3, maybe. So this is probably a little less than 1. Okay, but if I square these coordinates and add them up to 1, they should be 1. But it lives, okay, it lives on the sphere, right? The sphere is a d minus 1 dimensional object. Okay, so I could think of it as living in SD1. Sometimes you write it that way, and then that's a d minus 1 dimensional manifold, but it is a vector in R3 or in RD in general. In order to take a dot product between A and U, they need to be the same dimensionality. I'm not. The surface of the sphere would go through this point here, but the projection of A can go onto the extended U extended out, this line through U. This is a one-dimensional line that goes through d-dimensional space. Like the disco pose, right? Okay, so the sphere would be like this. I don't know what sort of dance this is, but it's a one-dimensional lower subspace. This is a one-dimensional space I'm projecting onto. This is a one-dimensional representation, but if I add the U, the times U, this is a scalar times a d-dimensional vector. So I'm back in RD. It's important. This is an RD, so I can measure this distance here. Whereas this is a one-dimensional representation. Okay, so now let's do this in down from 3. So again, we're going to get some point here. And now we're going to get 2. Now I'm going to take this. I'm going to call this guy U1. And this guy here, U2. What's going on here? I'm going to say that U1 is going to be a unit vector. U2 is going to be a unit vector. These are both in RD. Okay, but I'm going to add the restriction that the dot product between U1 and U2 is going to be exactly 0. That means that these are orthogonal so that there's a right angle between them. Okay, so I'm in D dimensions. Let's trying to think of 3 dimensions here. And there's 2 unit vectors, and they're orthogonal to each other. They're both unit vectors, but they're orthogonal to each other. Okay, so now I can define nicely, and in general, I will have F will be a subspace that's U1, U2 up to UK down to a k-dimensional space, where I will have UI and UJ. All of these are going to be orthogonal to each other. Okay, but let's just think about 2 of them here. Okay, and what I want to do is I want to project A onto the 2-dimensional space that slices through this 3-dimensional space. Project A down onto here. Okay, so A is going to be projected down. Let's see if I can try and draw this here. See if I can, let's decide it's here. This will be projection F of onto the subspace F defined by U1 and U2. So F will just be these 2 guys here in this example. Okay, and how do I do this? I'm going to say, well, I need to extend both of these lines for U1 and U2. And I'm going to say A projected, you need to kind of use your imagination a little bit here. But this is an orthogonal projection onto U1. And I'm going to get another orthogonal projection. So this would be pi of U1 of A. This is pi of U2 of A. And then they're going to form a 2-dimensional space here, which gives me pi of F. Okay, so so think of U1 and U2 as living in the plane of the board. A is kind of sitting up here, and I can project onto this line. I can project onto this line with A, and its overall projection is here. Okay, you kind of need to think like you have a perspective, and from 3D, you're probably sitting up here instead of, should have drawn it from your perspective down here, but try and work with it. There's a subspace that's going through here, a 2-dimensional subspace in green, and I'm projecting onto the subspace here. Okay, I can define that subspace by 2 orthogonal directions here, and I can define the projection in this way. Okay, so how do I define? I've defined earlier what pi of U1 of A and pi of U2 of A is, right? That gives me that tells me the length here is the dot product of A on U2, and this is A of U1. This dot product is up to here, and this dot product only goes so far, right? So this is the dot product onto U2. This is the dot product onto U1. It gives me kind of a length in these 2 coordinates individually. And now pi of F, okay, of A is going to be A U1 times U1 plus A dot product of A U2 times U2. Or in general, J equals 1 up to K of A dot product onto Uj times Uj. Okay, so now it's important that both of U1 and U2 are d-dimensional vectors, and A times U1 is a scalar. So this is a scalar times a vector. It gets me back this vector, which lives right here. And this one is also a scalar times vector U2, gives me this vector here. I can add together the vectors, and I get this pi of f, A, which gives me another vector here. So this lies in RD. This also lies in RD. I'm adding together k vectors instead of 2 vectors. It's examples with k equals 2. Okay, this makes sense? Okay, this is kind of the geometric picture you need to have in your mind of what we mean when we're doing dimensionality reduction. We are projecting onto a linear subspace in green here, and we can define a k-dimensional subspace with k unit vectors. And if they're orthogonal, then I can kind of write down the calculation very nicely. If they're not orthogonal to each other, I can define a basis of k vectors that are not orthogonal, and I can run Gram-Schmidt or something and make some set which spans the same subspace and still is orthogonal, and then I can do this. But in this lecture, we're not going to worry about that. We're going to assume we have k orthogonal unit vectors to define this. And we'll see how we get them in just a minute. Okay? This makes sense as the mechanism. If we have k orthogonal unit vectors, we can use them to project down to a lower dimensional subspace. Okay? What's neat here is I can write this term as alpha 1 and this term as alpha 2, and in general, this term as alpha j. And now I can also write pi of f bar equals alpha 1, alpha 2, and now this lives in R2. Okay, this is equal to the dot product of U1A, comma, dot product of U2A. And again, this lies in R2. I can use these two lengths along the first unit vector and the second unit vector to find two coordinates. And now if I want to be in a lower dimensional space, because this still lies in d dimensions, I can use just these length coordinates to give me a lower dimensional space. Now I only have two coordinates. And if I wanted to only draw a picture of these things, instead of trying to draw something in 3-dimension, I'm seeing a 2-dimensional projection of, I'm actually giving 2-dimensional coordinates. These are kind of my x coordinate and y coordinate here for U1 and U2. Right, so I can get two coordinates I can draw here as well. And it's a little confusing that this one gives me back a d-dimensional vector, this gives me a k-dimensional vector, but they're really doing kind of the same thing under the hood. I'm just kind of lifting this one back up. But it lives on this low-dimensional subspace in green here, similar to this one-dimensional subspace we saw with the dot product. Okay? Okay, so now let's write down the goal here, the sum of squared error, goal here, SSE. Okay, if you remember in the 3190 course Foundation of Data Analysis, you focus almost exclusively on the sum of the squared errors in that class. Here, we're going to say between A and the subspace F, I would like to look at the sum of the squared errors, AI in A, between AI minus the projection. Okay, so I want to minimize, the sum of the squared errors is the distance from each point A to its projected point. The fact that they're both in RD allows me to take a difference of vectors and to take the norm and to square it, right? And so the goal, the intermediate goal, this will not be PCA goal yet, but the goal is to find the k-dimensional subspace F, F star equals arg min F of the sum of the squared errors between A and F, right? So I want to find the subspace that minimizes the sum of the squared errors. Okay. And so, yeah, and in fact, if you think about this and you've seen gradient descent and stuff before, can I solve this with a convex optimization? Just sum of squared errors usually gives me a convex function. Maybe I can optimize this with gradient descent, right? You can't. The answer is no. Okay, you cannot solve this with gradient descent. Okay, the function itself we're optimizing is convex, but in order to represent F, we defined it as a subspace here. Let me try again on that one. Subspace. And we represented F as U1, U2 up to UK. And the fact that we force these to be where Uj is the norm of this equals to 1, and Uj prime equals 0, right? So if I defined it as these orthogonal vectors, forcing it to be a unit vector is not a convex constraint. So I can't actually solve this with gradient descent. But there's things called the power method and a whole bunch of other techniques how to solve for the subspace. In particular, we can solve with something called the singular value decomposition, the SVD, which at the start of class, everyone said they had seen the SVD before. So this is SVD will encode the solution to this problem. Okay, and we'll review how it does that next. This isn't the final goal. This is not, let me just put a warning on here, not the goal for principal component analysis yet, PCA. So we want to get to a PCA, which is not this yet. We're going to get to that. So this will be an intermediate goal. Okay, and then we'll get to PCA later, building on top of this. Okay, so we haven't yet defined the goal of the formulation of dimensional reduction in this class yet. Okay. All right, so let's, question. Okay, yeah, so there's, kind of, let me try and draw a picture here. We have now, instead of just one data point we're projecting, we've got a whole set of these data points, and we'd like to find a subspace through here defined by k unit vectors. So when I project each of them down onto this sum up, right, onto this subspace here, I want that what the sum of there's some subspace here that all these circles projection circles are supposed to go through, I want to minimize the sum of the residuals squared, the sum of the squared residuals. So it's saying I want to find the subspace that I lose as little as possible when I'm doing this projection. Okay, that's what this formulation is saying. Why do we do the sum of the squared residuals? It turns out we have an algorithm, the singular value decomposition, which returns the answer for this formulation. If I got rid of the squared, it becomes a much harder problem to solve. It's solvable still with the sum of the distances, but it's much harder to solve. If I want to minimize, say, the maximum distance or something else, it becomes even harder. So this is something that is solvable efficiently and has a lot of very nice properties that we'll be able to use this for many different variants of dimensionality reduction we'll see over the next few lectures. So it's a very powerful framework that is easy to use. One other thing we will see, though, is another formulation that has a different goal here that is trying to preserve distances instead of the sum of all the air from the projection. And that will give us a different formulation that in some way is harder, some way is easier and better. And there'll be another subtle difference between the singular value decomposition, which gives us sum of squared errors as defined here, and PCA, which we'll also see. Okay, so this is not the perfect goal, but this is one that has a very easy solution to it. So that's kind of the answer here. You should always be asking yourself, why do we choose this goal formulation? And so those are the litany of different ways to rationalize why we use this algorithm from the 1930s in order to do this, because we have a nice algorithm, basically. Okay, so sometimes the algorithm comes first and then the formulation comes later, and I think this is one of those cases. Yeah. Okay, so what is the singular value decomposition? Singular value decomposition. Okay, so what I'm going to do is I'm going to do the opposite of what we're doing in the streaming setting, where we have a data set, which, remember, this is A, and remember, this is N times D, and it's kind of big, and I'm going to turn it into something even bigger. So instead of getting kind of a summary, it's something useful, we're going to first blow it up into something larger than this. We're going to turn this into the product of three matrices. Okay, and this is going to be U. This first one is going to be in N by N. Remember, A is in N by D. So N rows and D columns. Now I have N by N here. Okay, the next one, S. Okay, S is going to be in N by D. That seems not so bad. And then finally, we're going to get another one, which we're going to call V transpose. It's going to be D by D. Okay, and we're going to have the property that we can write A as equal to U S V transpose, these three matrices. So I've taken one matrix, which has had a lot of data in it, was already big, and I've turned it into three matrices. One is the same size, one's even bigger, one's smaller. So at least that's good. But these have a lot of structure in them. Okay, the first thing to point out is that this S matrix, which is going to encode things called the singular values along here, and that below here is all zeros, all here is zeros. The only non-zero information is along the diagonal of the top B by D part, right? So S, I or say I is we're going to call the ith singular value. So this will be the ith singular value, and we're going to have the property that sigma I is going to be greater or equal to sigma I plus 1, and these are all greater or equal to 0. Okay? So it's got a nice property where these are decreasing in order along the diagonal, everything else is 0, and they kind of tell us how much information is captured in some way. Because this lower part, the n minus d part at the bottom is all zeros, that actually implies that a big chunk of u does not matter at all in recovering A, because this is multiplied by all zeros. So when I get A back, this part doesn't really matter. Make sense? I've multiplied by this all zeros part here. Sometimes, some way you write the code and it will output S as a diagonal matrix that's only d by d. If I do that, I can't multiply them back together again. I need to pad it with zeros so the multiplication works. Okay, but that tells me that this part of this matrix U doesn't matter. Okay, what else do we know about U? Well, we're going to write these columns of U as Uj, and Uj are going to be the property that Uj are going to be equal to 1. They're going to be these unit vectors, and Uj and Uj prime, the inner product of these is going to be 0. Okay, so this is nice. These look useful. So these columns here are all orthogonal to each other, and they're all going to be these unit vectors. These aren't so intuitive what to do with yet. They're size n. They're n-dimensional vectors. So I can't think of them as directions in my d-dimensional space. But these are called the left singular vectors. Okay. What will be more useful are over here. We'll call these Vj. Vj will also are going to be in RD. Vj, they're going to be unit vectors, and Vj prime is going to be equal to 0. So they're also going to be orthogonal to each other. Okay. So these guys are going to be useful because they're in RD. And in fact, these are kind of called the right singular vectors. Okay. And so this is the structure encoded in this singular value decomposition. Okay, so hopefully you've seen this before, and this kind of makes sense. I can write a bunch of nice properties here. I can write that AX is equal to USV transpose X, because this recovers X exactly. Okay. I can also decompose A USV transpose equals J equals 1 up to D. This is assuming D is less than N, otherwise you kind of reverse some stuff, times, which is the sum over Uj sigma J Vj transpose. Okay, so I can write it as the first left singular vector times the first singular value times the first right singular vector transpose. And then I do that for the second one, and second one, third one, and third one. Okay? Each of these terms, this is a little strange because I have these vectors. This isn't, when you multiply vectors together, I can write this as sigma j, uj, vj transpose, right? This, because I factored the singular value is a scalar, so I can pull it out. Usually when I multiply vectors together, I'm taking a dot product, right? Is that what's happening here? It's not a dot product. Why can't it be a dot product? What's the dimension of uj? Remember, what is the dimension of uj? N. What's the dimension of vj transpose? D. So I can't, how can I multiply together a n-dimensional vector and a d-dimensional vector? It's an outer product. It's not an inner product, which is a dot product. It's an outer product. So this term lies in n times d. This is an outer product of two vectors. Okay, so, well, this makes sense. I'm adding them up. I'm adding up terms, and they add up to something that's n by d. That means each of the terms must be an n by d matrix, scaled by sigma j, but this is a rank 1 matrix. Okay, it gives me a rank 1 matrix, but I add them up and I get a rank d matrix, assuming that the singular values are not, some of them are not 0. Okay, so I can write this matrix as a sum of these terms. The scalar is the singular values along S. Remember, S is all zeros here, all 0 in the lower part and the upper part along the diagonal are the only non-zeros. And each of these is a scalar value. It's a single value in here. Okay? Okay, so this sigma j, which I pulled out front, is a scalar value here. And this is an n-dimensional times a d-dimensional. I take the outer product, and if you can, from linear algebra, remember an outer product, I take, if I want to get the ith, jth coordinate, I take the ith entry of u and the jth entry of v, and I multiply those together, and that gives me the ith, jth coordinate. I don't add anything up. I just look at every pair of coordinates, and each of them goes with one cell in this n by d matrix. Okay, but it's a rank 1 matrix, but I add d of them up, and I can get a rank d matrix if A is full rank. If it's not full rank, then some of the singular values will be 0. Okay? So again, if you haven't had this in linear algebra, I know this will be going very fast, but okay, so now we'd like to get a low rank K approximation, okay, of A, and I write this as A sub K, which will be, again, a matrix in n by d. The same way we did this pi projection map that gave us back a point in Rd but it lived in a low-dimensional subspace. This will be a low-rank approximation of the full matrix, lie in a k-dimensional subspace, and I can write this as sum of j equals 1 up to k of sigma j uj vj transpose. So instead of summing up all the terms, I just sum up the first k of the terms. And remember that sigma 1 is greater or equal sigma 2, greater or equal ... sigma k greater or equal to 0. Right? So these are in sorted order. The u and the v vectors are unit vectors, so they don't encode any scale information. All the scale information, how much information does it capture, is encoded in the sigma values. And so I'll use the largest ones. And that will end up being a good answer, as it turns out. Okay? So I want to use the largest ones to approximate this. And so ultimately, this will give me my low rank approximation here. Okay, so I'm going to say that my low rank approximation F is actually going to be composed of the V1 before I introduce this as unit vectors U, but I'm going to use the right singular vectors to describe my subspace here. Okay, and so I want to kind of quickly go through a little bit of derivation to kind of see what's going on here. I'm going to sum up over all of the data points, AI minus the projection onto F. And I want to see what happens using the SVD to kind of analyze what this is doing. I want to project onto here, and I want to argue that projecting onto F, where F are the top K right singular vectors, that this will define the subspace that will minimize this sum of squared errors here. I'm going to do all this projection, take the distance, square it, and add all these up for all the data points in A, that this is going to give me the best. So let's kind of try and go through this math here. Okay, so we're going to add up. I'm going to now write the AI in the coordinate frame VJ dot AI, right? So AI, I'm going to rewrite as this. Okay, so what happened is I'm going to have my d-dimensional subspace is going to be spanned by d orthogonal vectors Vj. So instead of using the original coordinates, the x, y, z up to the d coordinates, I'm using a different coordinate system defined by these Vjs. And this is just recovering AI written in this coordinate system. Okay, it's the same point, just written in a different coordinate system. Okay, and now I can do this with the projection as well. Okay, Vj. What's different here is that the main difference that's happening here is now in the projection, I'm only using the top K of these because I'm only using the top K of these subspaces. Okay, and so I'm using the top K of them instead to write the projected version of A if I use this projection. Okay, now if I write this, a lot of these terms cancel because I'm summing over the same subspaces here. So what is left is Vj. In fact, instead of starting at 1, I'm starting at K plus 1 up to D. Okay, so the part that is remaining here is just the part that the first K I'm canceling, okay, in this subspace, and what's left is from K plus 1 to D. Okay, and now by the Pythagorean theorem, okay, I can say that the distance, I can pull this J, the sum of the J terms out. This is by the Pythagorean theorem. I can kind of decompose the sum of these things onto their things, right? This, you recognize the Pythagorean theorem measuring the sum of squared distance is the sum of the coordinates. I can use any coordinate system, and I've done this here to measure this norm. I pulled this out. I can now what I realize now is that this term captures no scale information. Okay, and so I can remove this out and simplify. I'm going to do two things at once. I'm going to switch the order of the sums, and I'm going to get Vj AI squared. Okay, this has no scale information, so I can pull it out. Then the norm, well, then this is just a scalar, so I don't need the norms anymore. That's just this term squared. Okay, now I can look at this guy, and I can write that J equals K plus 1 to D times, this is actually A times Vj squared. I can actually write this as, because I'm summing over all the terms in the matrix A, I can write the matrix A times this Vj. I'm multiplying by this vector squared, and this is actually equal to sum over J K plus 1 to D, and this is sigma J squared. This turns out is exactly the magnitude of the jth singular value. Okay, these singular values are taken, and so how they're constructed, one way of constructing them is you pick the first singular value as the direction that captures the most variation, and then I factor that out, I find the next one which is orthogonal to it. And so by looking at the projection onto any basis, well, I can, if it is the singular value basis, the remainder, the error, is exactly the sum of the squared singular values from K plus 1 to D, the ones that I've thrown away. So the singular values, the sum of the squared ones, actually captures this sum of squared errors or residual. And this is part of the nice structure that makes kind of this a nice thing to analyze. Okay, hopefully this is kind of review and you've seen calculations like this before. Okay, but this is kind of help explaining why the singular value decomposition is giving me the least residual possible by I'm just removing the smallest ones. Some of these might even be 0 if the data is low rank. Okay, hopefully this is illustrative a little bit. And so by taking these, this gives me the best rank K approximation. Okay, okay, so for who is this kind of new, this sort of calculations? You haven't seen stuff like this before. Okay, and the rest of you look kind of familiar, or? Okay, and some of you are kind of seen something like it, but a little uneasy with it, maybe. Okay. Let's see. Okay, so let me draw this picture again and try and kind of summarize what's happening in the picture. And hopefully this will review some, or at least help with the intuition a little bit. This one was S and V transpose. Okay, and if we remember that these guys were only interesting along here, and that this would be sigma J. These are the singular values. This was all zeros here, remember, and so this didn't matter because it was multiplied by all the zeros, although these are going to be unit vectors and orthogonal to each other and everything here. Okay, and then we're going to have these guys are going to be the left singular vectors. These are the right singular vectors here. Okay, and so now I want to choose the best rank K approximation, and that is I'm going to minimize the residuals of projecting all the points onto the subspace spanned by the vectors here. So I'm going to choose 1, 2, up to k. I'm going to choose 1, 2, up to k of these, and 1, 2, up to k of the left singular vectors. Okay, and then what I'm going to do is I'm going to take kind of this range here, this part of k, these top k things, and these top k. This and this pencil option I discovered I have. Okay. So these terms, this I'm going to write as u sub k. This part will be s sub k, and this will be v sub k transpose. And I will write together now a sub k is going to be u sub k, s sub k, and assume I padded it properly with zeros, v sub k transpose. And I'm going to recover something in RD and Rn by d because each individual term gives me an n by d matrix. I'm going to do k of them. And this will be the best rank k approximation, meaning the projection from the original points in A, the sum of the squared distances onto the subspace, this spanned by these guys, is going to be as the projection, sum of the squared projections is going to be as small as possible. The sum of the squared projections are going to be the part here that I have removed, and these are the smaller singular values here. Okay, and this is equivalent to if I just, this is equivalent to set sjj equals to 0 for j greater than k. So if I just set these terms equal to 0 and I multiply everything back through again, I'm going to get the exact same thing. When I set these to 0, what happens is then everything below here is 0. That means that everything up to here also doesn't matter because it's multiplied by all zeros here. And I get the same thing happen here, where everything below here also doesn't matter because it gets multiplied by these all zeros things. Well, in this case, down this way, right? Because now everything here is all zeros. So these get multiplied by something. So I basically can ignore these and ignore these. All that's left is v sub k transpose, the top k things here, and the left k things here. They are paired. If you remember, I could write it this way, where I recover this by summing over this scaling term, left singular vector, right singular vector transpose. And I can write them in this way to recover A. So they're paired in the construction because the middle matrix is only diagonal. So this one gets paired with this one. So the ordering is encoded through the singular values. Yes, correct. They are ordered by importance. In fact, there's a way of thinking about it where your data kind of lies, these are all of my data points. This is each AI. And so I can think of having an ellipse where this is V1 and this is V2, maybe V3 is coming out of the board, okay? And it's kind of defining some elliptical structure, ellipse structure that is fitting the data. And I'm scaling the ellipse. The amount I scale the ellipse, the length of this is basically sigma 1. And this scale is basically sigma 2. And coming out of the board, which will be shorter, is sigma 3 and so forth. And so this direction is, remember, is V1. This is the first right singular vector. So they are ordered in this way, and this is an appropriate way to think about what the SVD is doing. Yeah. Correct. Yeah, the right singular vectors are unit vectors. So are the left singular vectors, but one's d-dimensional, one's n-dimensional.
So what would
Yeah, it kind of is telling you how much each point is contributing to the norm of this right singular vector, or towards the norm in sigma 1. So it's n-dimensional, so that means every coordinate corresponds with one of the data points. And it's telling you how much that data point contributes to sigma 1. That's what the first left singular vector tells you. The second singular vector, these are orthogonal. It tells you how much each data point contributes to this. So it's a little bit harder to geometrically picture it, but you can just, everything you can do the transpose, and you can pretend it's d points in n dimensions, and then things work again. So maybe that helps. Maybe it makes it more confusing. But. Okay. Okay, so this is kind of the intuition you need. You wanted, let's kind of review what we had here. We want to do a dimensionality reduction where we want to output a mapping to a lower dimensional space, but it's also keeps it in d-dimensional space. You can do this through the dot product to get down to 1 dimension. Okay, to get to 2 or k dimensions, we can find a set of k orthogonal unit vectors, and that defines a projection down onto the space, right? So I can take every data point and project it down by doing it coordinate-wise for these u1 through u2 or up to uk, and adding these together because they're orthogonal gives me a different parameter space. It gives me a projection, but this lives in Rd still, or I can just write the lengths of these projections, and that lives in Rk. Okay? And so our first goal is to, yep.
why why do you jump straight to the sum of square error?
Because this is what we can optimize with the SVD. So let's say for now,
why we choose this instead of like min or max?
the SVD came first, and then people came up with this formulation. Well, I'll talk about at least one other formulation. Maybe more, depends how you categorize it, that different ways of defining what our objective is.
Yeah.
Yeah. No. This, if I use the pi bar, remember, the pi bar gives me the k-dimensional coordinates, just the lengths, but pi is the length times the unit vector. So I get me this vector. And then the second coordinate gets me this vector. These are d-dimensional vectors. They're orthogonal from the origin, and I add them up, I get another d-dimensional vector. I can measure distance between A and the projection. Good. Great question. I'm sure other people are confused. Okay, and now we're trying to minimize the sum of these squared errors. Let's say we want to do this. We're going to do this. We have an algorithm, the singular value decomposition, where we now have to define the subspace. Now I've switched from use unit vectors. It turns out you want to use the top k right singular vectors, which I now call v1 through vk, because I wasn't, this notation is pretty standard USV. So I switched notation in the middle of the lecture. Sorry about that. Okay, I think the book, maybe I was more careful about this. Okay, and I can now think of recomposing this as the kind of, I can add up the left singular vector times the singular value times right singular vector. This allows me to kind of recompose the point in a very similar way to what we did here. This is the left singular vector times the left singular value. The first right singular vector times the right singular value. The second right singular vector times the right singular value for a single point. But now I'm doing this for all points at once to add up the error. It turns out I can decompose them because we're using sum of squared errors. Pythagorean theorem allows me to decompose all these things because we're using sum of squared errors. This is one of the ways that's very nice. Okay? And now I can write this, I can minimize this error. I can see it, that's actually, the error is actually the sum of the singular values I threw away, I set to 0. Okay? And I can reconstruct it by just taking this part of the matrix. So using the SVD, I call this, you are probably not going to implement the SVD. You're going to call a function in a library. They all use the same backend code. Tran, you're probably going to use that code. We'll talk about next lecture a little bit why that might not be true, but for the most part, it's been true for 50 years. Everyone's used the exact same code in Fortran to compute these things with different wrappers around them. These define the subspace that I want to minimize the sum of the squared errors. Okay, and it gives me something like, good thing of projecting onto the ellipse. Okay, are we done? We haven't stated the objective that I want to state, which is the PCA objective. Okay, so we'll finish up, and I won't get to eigenvectors this lecture. It's okay. I'd rather make sure this is clear. I want to state the PCA principal component analysis. This is what you actually want to do for dimensionality reduction. Okay. Now I've got a set, we'll call this X, X1, X2, up to Xn, which is a subset of Rd. So an X I can write of as N times D. Okay, now my goal is to find a k-dimensional subspace. I'm going to call this B now. Okay, so this will be a k-dimensional subspace that that has a span of B is going to, the span's not the right word here. Yes, k-dimensional subspace is actually the technical right term. So k-dimensional subspace B, where if I want to minimize I equals 1 to n, xi minus the projection onto B of xi squared. Okay, so this is the PCA formulation, which if you don't understand some technical terms, I probably haven't described the distinction yet, looks exactly like the SVD formulation probably, or almost exactly like it. I've changed from A to X because we're going to have to map it into where we can use the SVD. But it looks exactly the same. The difference is best explained with the picture. Okay, so let me draw a picture here just in 2D. Okay, and now assume my data set A looks like this. Okay, so this is my data set X, where this guy is Xi. Okay, the data set Xi, I want to project this onto let's say K is equal to 1. Okay, I want to project it onto a one-dimensional subspace. I do this with the dot product, right? Kind of, but what can I do with the dot product? What would the vector U, how would I pick a vector of V1 or whatever to project onto here? Yeah, okay, I hear origin here, right? So I maybe would pick a direction V here. If I ran the SVD on X, this would probably be V1, right? And I could project onto here. The projection onto here now, right? This point projects onto here. And this is the direction which is minimizing the sum of the squared of these things. But this doesn't seem right. The data looks kind of aligned here. There's a one-dimensional subspace that runs through the data. So what if instead I found my subspace looked like this? What if this was B? Where now I'm getting a subspace that's very close, and the projection is now these things here. Yeah, so this makes a lot of sense, but the SVD will give me this vector here, this V1 vector. So the trick is I need to first center the data. What center the data means is I need to transfer it so that the data looks like this. I basically move every data point by the same vector. So I'm going to center to get AI is going to be xi minus a center vector, where C is going to be a vector in RD. Okay, so I'm subtracting C, this vector C, from every data point here to get a new data point AI. Right, once I do that, then I can run SVD on A, right, is going to output this V1 prime, which is V1 prime, right? Once I transfer them so they're more centered, okay, then I can run the SVD and I can get out this one-dimensional subspace or a k-dimensional subspace if I wanted to. How do I choose this vector C? It's just the mean. The right thing is to mean is I do C is 1 over n, I equals 1 to n of xi. This is the mean. Okay, so I just subtract the mean off of every data point. I get back a vector AI. This is true for every data point. This is now gives me a vector, a matrix A is A1, A2, AN. Okay, I run the SVD on A, and now the subspace I get out of there turns out to be the one that minimizes this. This algorithm where you center and then run SVD is called is PCA. Okay, so PCA is 1, I center, 2, I do SVD, and 3, I return V1 up to VK. Okay, the subspace defined by these, right? The top K right singular vectors, and I can project onto those. Okay, so there again, you'll find some stuff online. It's better since I started teaching this, at least. I don't know if I had a help or not, but it used to be that people would confuse SVD and PCA. They'd say you want to run PCA, you just call SVD, take the top right singular vectors. PCA you should center first, and this can make a huge difference. Okay, so oftentimes people will run SVD, and the first right singular vector will be a very large value that will have 90% of the error, 95%. This often happens, perhaps, if your data set is filled with positive only values, no non-negative values. Well, then the data is actually going to be in this first quadrant. Everything is going to be up here. And so the first singular vector is just going to point up into that first quadrant and not tell you anything useful. And it's not telling you where that low dimensional subspace is. You first want to center, remove that average value, and then run the SVD to get the right singular vector. These are now called the principal vectors. And the corresponding singular values of these centered data points are the principal values instead. Okay, this is different, and it can make a very big difference in some data sets. SVD kind of assumes the data set's already centered. It's a linear algebra operation, so in that sense, it doesn't really care, but it's modeling it for subspaces as if it was centered. Okay, so our first dimensionality reduction approach is PCA, which is basically centering and then calling the SVD, which does all that magical stuff we talked about earlier on in the lecture. Okay, great. homework for streaming due Wednesday, but if you're running behind, let me know and I'll probably be flexible. And we'll talk about other approaches in this world and we'll go a little bit slower because this should have been review for most of you. So we'll go a little bit slower now that we've gotten back up to speed.
Did you return the midterm at the beginning of?
It should be on grade scope. Let me try and find a end the light.